Hello there, welcome back to Star Stuff, where we are continuing the series explaining the hard to understand stuff. The series where I try to explain complicated science in a really simple way. This week we are explaining time dilation. Did I just say we?
You did, and I'm here now, so you're welcome.
Dan, I didn't. Okay, fine. This might actually work out perfectly because I can't possibly do this by myself. So you'll just have to do.
Perfect. Time dilation.
Let's explore this. Time dilation is the phenomenon where time passes at different rates, depending on your speed, which is special relativity, or your proximity to a massive object's gravity, which is general relativity.
Both forces stretch time relative to a stationary observer, but they operate under different physical rules.
Let's focus in on how speed affects how time passes. This is called kinematic time dilation, which is a super scientific way of saying if you go fast enough, time itself starts behaving differently. There's an uncomfortable truth in this. It's that time doesn't pass at the same rate for everyone. This comes from special relativity, developed in 1905 by Einstein, a man who said, "You know what would be fun? Let's completely ruin everyone's understanding of time." Kinematic time dilation happens because of velocity. The faster you move, the slower time passes for you relative to someone else. And no, I don't mean like speeding on a highway. This is talking about speeds closer to the speed of light, which is about 300,000 kilometers per second. So why does this happen? The speed of light is constant for everyone, no matter how fast you're moving. And this is exactly where reality starts to bend a little. Because the speed of light is always the same, then something else has to change to make that work. And that something else is time. Think of it like the universe having a strict rule. Light must always move at the same speed. So if you try to move really fast, the universe goes, okay, I can't change the speed of light, so I'll just slow your time down instead. Physicists use something called a light clock. Imagine a photon bouncing between two mirrors. Each bounce equals one tick of a clock. Now imagine the clock is sitting still. The light just goes straight up and down. Now imagine the clock is moving sideways at high speed. The light doesn't go up and down anymore, it goes diagonally. Because while the light is moving up and down, the whole clock is moving sideways, so the light has to travel a longer path. The speed of light hasn't changed. If the light is traveling a longer distance, it takes more time to complete one tick, which means the moving clock ticks slower. And since everything in that moving system follows the same physics, time itself is slower. Imagine you get into a spaceship and you travel at 90% of the speed of light. To you, everything feels normal. Your heart beats normally, your watch ticks normally, you snack normally. Very important. But to someone watching from Earth, you're moving so fast that your time appears slowed down. So when you come back, you've aged less than everyone else. Which means you didn't just travel through space, you time traveled into the future. This leads to one of the most famous thought experiments, the twin paradox. The one twin stays on Earth, the other twin hops in a spaceship and zooms off at near light speed. They eventually come back and reunite. The weird part is the traveling twin is now younger. Hey, I just got back from space. Oh, cool. I just aged 30 years while you were gone. Now, technically, it's not a true paradox because relativity does explain it fully, but the name stuck because it makes your brain do backflips. If this still feels like sci-fi, we've tested this with real experiments. There was an experiment called the Hafele-Keating experiment. Scientists took atomic clocks, put them on aeroplanes, flew them around the Earth, and compared them to clocks on the ground. The result? The clocks on the ground were slightly behind. Time literally passed differently for them. Also, particles called muons live longer when moving at high speeds. They should decay quickly, but because they're moving so fast, their time slows down, and they survive much longer than expected. So here's the part where physics flexes. There's an actual equation for this. Time dilation depends on your speed relative to the speed of light. The closer you get to light speed, the more extreme the effect becomes. At 10% light speed, it's barely noticeable. At 50% light speed, it's noticeable. At 90% light speed, it's significant. At 99.9% light speed, things get ridiculous. At extreme speeds, you could experience hours while years pass on Earth. You're probably thinking, "This tomorrow drought we must." But unfortunately, we as humans cannot accelerate at the speed of light. It's the universe's way of saying, yeah, no. So kinetic time dilation tells us something profound. Two people can experience different amounts of time and both be completely correct. So time isn't broken. It's just not what we thought it was.
But time will also pass at different rates under the influence of gravity. Okay, imagine you have two identical clocks, one sitting on the ground in front of you and one sitting at the top of Mount Everest. Now, the flat earth phrase of choice, common sense, says that those clocks should tick at exactly the same rate. But they don't. The clock on top of Mount Everest will run that tiny little bit faster. Not enough for you to notice, not enough to make you late for the next flat earth meetup either, but enough to be measured. So why does that happen? Well, Einstein discovered, of course, that gravity doesn't just affect things like apples and planets, it also affects time itself. The stronger the gravity, the slower time passes, and the weaker the gravity, the faster time passes. And because that clock on top of Mount Everest is a little bit further away from the Earth, gravity is slightly weaker up there than it is at the surface. The obvious question though is, why does gravity slow time down in the first place, right? And it's not because it watched a Nathan Oakley livestream and became cosmically bored. It actually all comes down to how Einstein thought about gravity. He discovered that space and time are connected together in something called space-time. You can think of space-time as the very fabric of the universe, and everything that resides in it sits inside space-time. Planets, stars, galaxies, even you and me. Now, anything with mass will change the shape of space-time around it. And when you get something massive enough, like a planet or star, it significantly changes the space-time around it. So when space-time changes due to a massive object, time changes too. The stronger the gravity, the more space-time is distorted. The more space-time is distorted, the slower time passes. Let's think about a road for a second. Imagine that one car is driving along a perfectly straight road, and another car is driving along a windy mountain road with lots of turns and twists. Even if both cars are trying to travel at the same speed, the winding, twisting road changes their journey. Einstein showed that massive objects twist and distort space-time in a similar way. And because time is part of space-time, the flow of time changes too. And that is why the clock on Earth's surface ticks more slowly than the one on top of Mount Everest. The film Interstellar shows us the human cost of this phenomenon quite beautifully. In the film, Cooper and his crew travel to a planet orbiting extremely close to a massive black hole. Now, because the gravity is so intense on that planet due to the black hole, time travels much more slowly there than it does for those further away. And the consequences are devastating. The crew spent only a few hours on that planet, and over 20 years had passed for the colleague they left behind. Now, yes, Interstellar takes this effect to an extreme, but the science behind it is absolutely real. Einstein showed us that time is not the same for everyone. It can speed up and it can slow down. And under the right conditions, two people can experience completely different amounts of time between the same two events. It's also a pretty solid excuse for being late, but I wouldn't recommend trying that one on your boss, unless you want to show them this video. So, bringing this all together then, gravitational time dilation is a direct consequence of Einstein's theory of general relativity. Now, you don't need to worry that climbing a hill is suddenly going to catapult you into the future. The effects here on Earth are tiny, but they are real and we have measured them. It is, in my opinion, one of the strangest, most beautiful, and most thoroughly tested ideas in all of science. Time itself is not fixed. It's literally shaped by gravity.
So all in all, we're basically part of a universe where time bends depending on how fast we move and how strong gravity is.
So how fast does time move then next to the regular flat earther brain?
Well, you see, we haven't come up with the physics to understand that type of speed just yet. What we do know is that relativity changed how we understand reality itself.
And if we can understand reality better, then maybe that can go a long way to understanding ourselves.
See, I knew there was a good reason to have you on this episode. It was all my idea. Thank you so much for watching. If you enjoyed this explainer, please don't forget to like and subscribe. And thank you, Simon and Dan.
You're always welcome. Thank you for having me.
Cool beans.